On the news and in social media, it was called Stormaggedon. A ferocious weather event that tore down Australia's east coast in the first week of winter. In just a few days, it wreaked havoc from Queensland to Tasmania. Waterfront foundations were swept away. Extreme flooding caused deaths, widespread road closures and evacuations. As the clouds cleared, the debate began on whether Stormaggedon was truly a weather system out of the ordinary or part of a new trend.
Certainly in the last 50 years, we haven't really seen any trends.
That's the sort of thing we're going to see in the future.
The subtle shift makes the storms more intense.
How are storms changing across Australia? And is this a taste of our climate change future? There's nothing unusual about an East Coast low, the type of storm system that usually batters eastern Australia between late autumn and winter. But right off the bat, forecasters at the Bureau knew this one was going to be big.
So the system started on the 3rd of June, quite typically, just off the coast of southeast Queensland. But after that, it started to become unusual. So it interacted with quite a deep trough extending from New Caledonia up in the northeast, right through the Tasman into southern New South Wales. In terms of the spatial footprint of this system, it was very unusual.
An intense, stationary high-pressure system over New Zealand was blocking the East Coast low from spinning out to sea and driving it south.
Normally, we tend to have one or two parts of the coast really copping the brunt of the storm, but for this one, it really tracked all the way down. So we had flooding across catchments right down New South Wales, Victoria and Tasmania.
By Sunday, Tasmania was underwater.
And I moved the dairy cows from here on some of the high ground, and there was 320 stranded, and then the water just exploded, just come from nowhere. And then I come back at 3 o'clock in the morning, they were all gone, they're all washed away.
What we saw was record rainfall over 3 days, and something like 5 rivers in flood at the same time in northern Tasmania, and that's quite unprecedented. And really the sheer volume of water was really reflective of just how much water was in the atmosphere.
Heavier rainfalls normally occur in warmer months because a warmer atmosphere can carry more moisture. In this case, it wasn't just the atmosphere, but the seas were also abnormally warm.
For May, the Tasman Sea was almost double its previous record. So we had really very high sea surface temperatures in the Tasman. You saw this system basically sitting off the coast, directing the airstream over that warm water into Tasmania.
Would you say that the warmer weather definitely played a part in how much rainfall Tasmania got?
Those sorts of attribution studies take some time, but certainly just based on a basic understanding of the meteorology, then the things line up quite closely.
So this was definitely an unusual storm in its size, with warmer than normal weather conditions likely contributing to the extraordinary rainfall. But surprisingly, these East Coast lows are predicted to decrease, not increase in frequency as the climate warms.
And that's largely because the atmosphere becomes a bit more stable under climate change. So both the tropical cyclones and East Coast lows, there's an overall likely reduction in number, but the proportion of these heavier storms tends to increase. And that's because when the meteorology is right, we've just got that much more energy for the storm from the sea surface temperatures underneath.
A team at the University of New South Wales have also found tropical expansion from climate change is likely to push more East Coast lows off the mainland.
We're likely to see a shift of the storm tracks to the south. And that just means that, we're still going to get storms, they just won't hit. They'll hit further south than they currently do. So that's why we might see a decrease in the frequency of them. A decrease in frequency doesn't mean a decrease in damaging events, because what we're saying is climate change will also bring rising sea levels and bigger waves.
Big waves and high seas were a major damaging force in this recent storm, and they took particular aim at the southern end of beaches. Some of the most spectacular damage was seen here at Collaroy in New South Wales.
This is the largest erosion event that I've seen in my career working on the Australian coastline. We saw the beach narrow by as much as 50 metres. We saw a swimming pool on the beach. A lot of sand was moved.
I'm standing here on a rock wall that was built to protect the property behind me. Usually you can't see any of these rocks because the sand completely covers them.
In total, around 40 metres width and several metres depth of sand disappeared from the beach. But apparently, it all comes back. For the last 40 years, a team from the University of New South Wales have been using a variety of imaging equipment to map this shoreline.
We use conventional survey equipment, we have cameras mounted on rooftops, we fly aeroplanes with a laser scanner, and we fly drones. What we're trying to understand is how the sand is moved by the ever-changing wave and water level conditions. Over the 40-year monitoring program here at Narrabeen Collaroy, there's actually been no sand lost.
Although the beach has shifted in shape, the overall volume hasn't changed.
Sand is stripped from the dunes and deposited out in the sandbars, but it always comes back.
It's small comfort to those that just sustain severe property damage from such a big erosion event.
So what has made this storm in particular so diabolical?
Well, there are three things that have come together over the weekend. First of all, we had large waves. So waves were recorded offshore Sydney on Saturday night up to 13 metres. But by coincidence, those large waves coincided with king tides. It's over 2 metre tides, so that brought the water level high. And then the third thing, which is perhaps most unusual, is the storm direction. The storm came from the east-northeast, and that's relatively unusual for our stretch of coastline, and it exposed areas like this that generally a bit more protected, exposed them to that wave energy.
So why is it coming from that direction?
Oh, look, it's just how the East Coast low storm developed. It's a natural process, it does happen. That one happened to come from the northeast.
While the king tides were nothing to do with warmer weather, they do give a good picture of what future sea level rise might look like. And the other two factors of this mighty storm surge, big waves and a northeast swell, might be a shift we can expect more often. It couldn't look less like Stormaggedon at Hawke's Nest in New South Wales, but it's here I'm starting to understand why the northeast shift had such a powerful effect.
This black nor'easter generated waves 1,500 kilometres away, almost into the Coral Sea. These long wavelength waves, as they moved across the continental shelf, were shoaling to produce very high wave heights. 15 to 25 foot faces were surfed during this period and produced the storm erosion along the coastline.
So why do they call it a black nor'easter?
Black nor'easter refers to the skies go black, dark grey, the winds are gale force. We don't think of high pressure systems capable of producing storm waves. But when those high pressure systems become really intense, the winds off them produce these large waves. And when combined with an East Coast low, they produce the most extreme storm wave environment.
Normally, we think of a high-pressure system as bringing calm and lovely weather like today, but the intense high over New Zealand not only squeezed Stormaggedon into the coast, it fueled it with the intense, warm, moist winds that brought such dramatic rainfall. GOODWIN is a paleoclimatologist, and as he digs into our stormy past, he's convinced we'll see more and more of these big blocking highs and black nor'easters.
When most of us go down to the beach, we see sand. But for us, we look at the sand much like someone studying tree rings, or if we're studying the layers in an ice core, that each successive period of coastal deposition or erosion is actually recorded within our undeveloped coastline. We use aerial LiDAR to produce fine resolution digital elevation models, and then we use ground penetrating radar to look into the sand deposition. We then need to know when each of these periods occurred. When a sand grain is deposited by waves on a beach and then buried by the next wave, its clock, or how long it's been buried, starts at that point. And the quartz grains in that sand and the feldspars attract radiation from the surrounding heavy mineral sands. We then come along and we want to extract a sample in total darkness, bring it back to the laboratory, and then measure how much radiation is in that quartz grain and hence use it as a clock.
It's like developing an ancient sand grain photograph in the darkroom. Depending on how successive layers of the beach were deposited and when, it reveals the dominant wave and wind patterns throughout history.
One of the things I got excited about when I saw that storm developing was that was the type of system that we had reconstructed as being much more frequent during the period from about 1650 AD to 1800 AD.
During each stormy period when the black nor'easter was more frequent, it was also a period of tropical expansion. And that's what's happening in today's climate.
It's quite a straightforward understanding that as the tropics expand, the subtropical air masses are influencing more of the East Australian coastline, and that combined with low pressure systems coming out of the Southern Ocean produces more of these storms that approach our coastline from the east through to the northeast.
If Ian's predictions are right, the explosive wave, wind and rain combination of Stormaggedon will become a more regular feature of our climate change future. It may leave the southern ends of beaches particularly vulnerable to property damage. While storm surge affects those close to the beaches, it's flooding from torrential rains that can grind whole cities to a halt.
In an urban flooding environment, you can't go for shopping, go to work. Your day-to-day civil life that you take for granted is put on hold. And this has a massive disruption on the way society functions.
Like many other streets, Botany Road looked very different under heavy rainfall last month. The rain simply came down too fast.
There we go, help's on the way.
The reason any urban area floods, it's not because of the amount of rain that comes down by itself, but it's the rate of the rainfall. If the rate is really high, the urban area, the stormwater infrastructure that is in place cannot cope because the water has no other place to run off to.
At the University of New South Wales, Professor Sharma and Conrad Wasco have been looking at how rainfall patterns have changed over more than 40 years.
We looked at a collection of storms, something close to 40,000 storms across Australia, all climate zones in Australia. And we found consistently the storms were getting more intense, more concentrated in time and in space. And this is what is so impactful. This is why the study has been noticed so much across the world.
As storms shrink in space and time, stormwater systems increasingly fail.
Get this 2 or 3 minute bursts of rain that are massive. This peak flood cannot anymore be contained by the infrastructure that was designed many years ago to withstand a flood that would be spread over a longer period of time. And we found a 100% result. All the locations that we looked at were finding exactly the same pattern, that the storms were intensifying with warming climates.
The research here at the University of New South Wales is the first to show that flooding from storms will increase in cities due to climate change. We can never blame any single storm on climate change, and the so-called Stormaggedon is no exception. But it's an interesting example because its influences include warmer, higher seas and a warmer atmosphere, all predicted to intensify the effects of storms in the future. So what, if anything, can we do to prepare? When it comes to floods, hanging on to our green spaces within urban environments is vital to cope with more intense bursts of rain.
If you have that storm fall on concrete, it will come out as a very intense flood. If this storm falls on to a landscape that can absorb the impact of the storm, it will dampen the flood peak that just stretches the flood out to a longer time span. If the flood gets stretched, then that intense peak that you were having, that comes down.
With greater storm surge due to sea level rise, we may need more mitigation strategies like beach replenishment. But ironically, bigger storms from the northeast may help with that.
Storms are seen as evil. They're the bad guys because we see what they produce in terms of storm erosion, and we look at houses falling into the ocean and so on. But in fact, whilst they are causing that erosion, the higher wave energy out in the deeper water is actually mobilising sand on the seabed and helping to transport that towards our coast. So a decline in storm activity means less sand transported to our coast, and hence our coastlines would recede faster with sea level rise. So we need to wish for more storms.